Hey guys, we're about to do chapter 21. We are following the first half of chapter 14. Again, once we introduced zero order, first order, second order, and did some of the calculations related to the amount of sample and how much time it takes for a reaction to occur, that's a good time to introduce nuclear chemistry, where we're going to do half-life calculations and aging samples that are either hundreds or thousands or millions of years old. Nuclear chemistry, all the chemistry we've done up till now has been focused on reactions that are what we call normal chemical reactions. Normal chemical reactions are reactions where we are forming and breaking chemical bonds that relate to the valence electrons of an atom. Now, hopefully you know, valence electrons are around the nucleus, and we can either lose electrons, we can gain electrons, or we can share electrons. But in none of those reactions have we really dealt with the nucleus directly. Okay? Now this chapter, chapter 21, is going to focus on what happens if a nucleus made up of protons and neutrons, what happens if it's unstable and a piece of it breaks off. Okay? That's going to be the definition of what nuclear decay is. Radioactive decay, also called nuclear emission, is when a piece of a nucleus breaks off and flies away. Okay? So, a nuclear reaction is any reaction that actually changes the nucleus of an atom. This is going to be a place where we're going to distinguish different isotopes of elements, because they actually, in nuclear reactions, different isotopes will behave differently. Okay? Like carbon has 3 different isotopes: carbon-12, carbon-13, carbon-14. Those 3 isotopes make up all the carbon and everything around us. Okay? In normal chemical reactions, those isotopes all behave pretty much the same. When we breathe in CO2, whether it has carbon-12 in it, or carbon-13, or carbon-14, doesn't really change how it behaves in our body. Okay? We can eat glucose that has carbon of all isotopes. Our body will break it down into CO2, and then we breathe it out. What isotope it is doesn't really matter. Okay? But when we talk about nuclear reactions, then the isotope is very important, because carbon-12 and carbon-13 are actually stable isotopes that don't normally undergo nuclear reactions. But carbon-14 is a radioactive isotope. Over time, it will actually go through a nuclear reaction, which is shown at the top, and it'll actually be converted into nitrogen. Okay? So, different isotopes are significantly different in nuclear chemistry. Now, natural nuclear reactions are happening all around us, specifically with unstable nuclei. So if a nucleus is unstable, those are the ones that are going to spontaneously decay. But some of these are going to happen quickly if they're really unstable nuclei. Some of them are going to happen over millions of years. Okay? And that's some of the stuff we're going to study. Now, how quickly those reactions happen is something that we can't really control. Carbon-14 has a half-life of 5,730 years. There is nothing we can do to change that number. And what that is, like half the reaction, half of the carbon-14 in a sample will react and turn into nitrogen in 5,730 years. Okay? It doesn't matter whether the carbon is in the form of CO2, or if it's carbon in a diamond, or carbon in glucose. That has no bearing on how long it takes for carbon-14 to break down. Okay? So we can't control that. We can't change it. Now, there are natural nuclear reactions, which is our main focus in this chapter, but we will touch a little bit on some artificial nuclear reactions, which would be like fission and fusion bombs and stuff like that. Now, one of the reasons that these reactions are really important to us is that these reactions involve huge energy changes that are several orders of magnitude greater than normal chemical reactions. Now, why is that important? Well, basically the natural processes that are around us, even though only a few atoms at a time are breaking down in those slow processes, the amount of energy that comes out is significant. And if you're exposed to much of it, it can be a source of cancer. and other health-related issues. Okay? If we can concentrate the samples into larger amounts, then that creates the possibility of nuclear reactors and nuclear bombs and stuff like that. So it's a very important field of science, specifically related to the energy changes that are occurring. Now, a little bit about the history. It was the late 1800s. There's a guy named Henri Becquerel, French guy, in his research lab. Marie and Pierre Curie, I'm sure you've heard of them, were graduate students. But they kind of accidentally discovered radioactivity, where they left a radioactive sample on a table over a weekend, I think, and they left a photographic plate nearby, and basically over the weekend they came back and the photographic plate had spots all over it. And they figured out that the spots had to come from the sample they left on the table, and they figured out that it was spontaneously emitting particles. And they were studying other aspects of that sample, but when they realized that, that was the first time that radioactivity had been observed directly coming from a sample. And that sample had a lot of heavy metals in it, which heavy metals tend to be rich in radioactive isotopes. So, to do these, we're going to learn to write reactions first, and then we'll get into the math stuff later. We need to know what the particles are that we're going to be writing about. So, again, if you go way back to chapter 2, we introduced alpha particles, beta particles, and gamma particles. So we need to know what those are. An alpha particle is basically a cluster of 2 neutrons and 2 protons stuck together. So the mass of an alpha particle is 4. 2 protons, 2 neutrons, they all weigh 1 AMU each. The charge, the 2 protons have a +1 charge each, so the charge is positive 2. And if I have a cluster of 2 protons, 2 neutrons, if I were to assign that an identity, that's basically the nucleus of a helium atom. You know, it's a cluster of particles with 2 protons. So the symbol we use is helium. So this is the nucleus of a helium atom. That's essentially what an alpha particle is. In nuclear reactions, it shows up a lot. That's why we've kind of set that one aside as a special case. But we need to know what an alpha particle is. You can represent it by the symbol alpha, or you can write out the atomic symbol that is shown here. A beta particle is an electron. So again, the symbol, the mass of an electron compared to protons and neutrons is a lot smaller, so we call it 0. The charge is -1. So, and we use the lowercase e for the symbol, so that's how we write an electron. A gamma particle is actually a photon of high energy light. So if we wrote the symbol for a gamma particle, the mass is 0, the charge is 0, and then we use the gamma symbol. So make sure you know how to do that also. And then there are other particles that come up. A proton is a mass of 1, a charge of 1. And then most of the time we're going to go ahead, kind of like with the alpha particle where we call it a helium nucleus. With a proton, we're going to call it a hydrogen nucleus. Okay, so it's 1,1H. It is okay to use a lowercase p to represent the proton. The problem with that is a lowercase p and a capital P for phosphorus kind of look similar, and that could be confusing. Okay, so we'd rather use the hydrogen symbol to represent a proton instead of the P for proton. Okay, and then a neutron, again, it specifically has to be a lowercase n. If you use a capital N, that's nitrogen. The mass is 1. The charge is 0 for a neutron. This is a very brief list of particles. There are a lot more particles that could come up. If you go into a medical field that uses radiation, like mapping and x-rays, and if you're a radiation technologist, they do PET scans. A PET scan is a positron emission tomography. So then you need to know what a positron is. A positron is basically an electron with a positive charge. Okay, so that's kind of weird, but that is a real particle that exists. Now, which elements are radioactive? Well, first of all, there can be radioactive isotopes of any element, okay? But specifically when we deal with our smaller elements, and so Z stands for the atomic number. If the atomic number is less than 20, the most stable isotopes tend to be the atoms where the number of protons and neutrons are about equal to each other. So if we think about, for carbon, the most common isotope of carbon is carbon-12. It has 6 protons and 6 neutrons. That's a stable isotope. For oxygen, the most common isotope is 16. That's also a stable isotope. It's 8 protons and 8 neutrons. Neon has 10 protons and 10 neutrons. Okay? So those are all stable isotopes. When we look at carbon-14, which is an unstable isotope, it has 6 protons and it has 8 neutrons. Okay? And just that imbalance is common for smaller atoms. When the protons and neutrons are further apart from each other, it's more likely to be radioactive. Okay? We're really not going to get too much into predicting that in this section, but just realize there are rules that can be followed, that it's not a bad thing to be aware of. Now, the heavier atoms. So when we get down near the bottom of the periodic table, what you'll notice with those is that if we do have a stable isotope, the number of neutrons is going to be a lot bigger than the number of protons. Like if I look at a silver atom, the most common isotope of silver I think is 107, and the atomic number is 47. So that means it has 47 protons and it has 60 neutrons. The further down you go, the more different they become. The neutron number gets to be much larger than the proton number. Okay? But if we get down below atomic number, the atomic number is greater than 83, which is bismuth. Any atoms bigger than that, basically they don't have any stable isotopes. Once you get above a certain size, the nucleus is just too big and bulky. None of them are stable above 83. Okay, so the largest atom that is commonly found that has stable isotopes is lead. Lead-206 is the biggest atom that exists that we know of that is stable. And then when we get above 92, we get to atoms that actually don't even exist on Earth in any appreciable amounts. So those are artificially produced. So 92 is uranium. Basically above uranium in terms of atomic number, we don't see those elements in nature, but we can produce them through chemical reaction, or nuclear reactions in a lab. So again, the ratio protons to neutrons, for small atoms, they tend to be about the same. The bigger the atom gets, the more the neutrons have to dominate. So this is called the belt of stability. Don't worry about it too much for now, for 1212. All right, so our different kinds of nuclear decay. If an atom is unstable, it will spontaneously give off a chunk of it that'll break off in the hopes that it'll become more stable that way, okay? So an example of an atom that does that, uranium-238, which contains 92 protons and 146 neutrons, okay? That atom is unstable. Over time, if you have a sample that has a lot of uranium-238 atoms in it, every once in a while, one of those atoms will just have a little chunk of it that'll break off and fly away. That chunk is going to be an alpha particle. So I go from uranium-238, I'm going to have an alpha particle that breaks off, which means that I'm losing from my original atom, I'm losing 2 protons and 2 neutrons. So then I can figure out my new atom that I have is what's left. Well, I had 92 protons, now I only have 90. I had 146 neutrons, now I have 144. And my new mass is now only 234 instead of 238. Okay, so I can write this out as a reaction as shown right here. Uranium-238, when it splits, I'm going to get an alpha particle, and then the math is pretty easy. If I just look at the top, the total mass, 238, When I look at my products, I have to account for all that mass. It'll be 4 for the alpha particle plus 234 equals 238 that I started with. I also have to maintain the balance of charge. Whatever my charge is on the left side, which is the protons, 92 protons, when I go to my right side, it's going to be 2 plus 90. So I know the numbers on the top of the equation have to be balanced, and the numbers on the bottom have to be balanced. If you do one of these reactions and you have to figure out what a missing particle is, you just look for how many, like whatever the number is you're missing on top, whatever the number is you're missing on the bottom. Once you know what the atomic number of the bottom is, then you can figure out what the element is that you should be putting in that spot. We'll do some examples of that in a little bit. Now, next example, alpha decay, we lose an alpha particle. Beta decay, we lose a beta particle. Now, how does this happen? Well, if you think about it, we're doing a nuclear reaction. A nuclear reaction is, we have particles coming out of the nucleus. So when I tell you that an electron is coming out of the nucleus, that should strike you as a little bit weird or strange. Okay? Because in the nucleus, we've always learned it's protons and neutrons. So where does the electron come from? Well, it involves, and again, you had to get into particle physics and all that kind of stuff to really explain this fully, but a neutron is actually the combination of a proton and an electron. If we fuse them with each other, that's what a neutron is. There are some other particles involved with that are even smaller, that are like quarks and muons and all that kind of stuff. But think about the proton has a massive 1 and a charge of 1. The electron has a mass of 0 and a charge of -1. When I combine them, the mass is 1 plus 0, which is 1. The charge, 1 plus -1, is 0. If my mass is 1 and my charge is 0, that's what a neutron is. Okay? So, what happens in a beta decay or a beta emission is that one of the neutrons will spontaneously just break apart. The electron flies out of the nucleus, but the proton stays. So essentially, we're turning a neutron into a proton as an electron flies out. Okay? Now, when this happens, the atomic number, which is the number of protons, is going to go up by 1 because we lost a neutron. Neutron goes down by 1, proton goes up by 1. Okay? So then if we look at the reaction, what we'll see, if I turn a proton to a neutron and an electron flies away, the mass didn't really change. It was 131 over here, it's still 131 over here. But my atomic number went from 53 to 54 as the electron flew away. Now, even if you get confused on the electron coming from a nucleus and making a proton and stuff, again, if we just focus on the math, it can all be figured out. So, let's just say if you were told iodine 131 undergoes beta decay, you know that iodine 131 is your starting material, your reactant. So you write iodine 131, the atomic number is 53, so you write out your symbol. On the product side, if it says it's beta emission or beta decay, you know that an electron is a product, so you can write that down. And then you just look at the missing particle and say, okay, what am I missing? My mass on that side is 131. Over here, my electron has no mass. So this particle has to weigh 131. So there's the 131. My charge on this side is 53. On this side, I have a -1. So what does it have to be? Well, it has to be 54 minus 1 to give 53. So this has to be a 54. And then knowing that's a 54, I can look at the periodic table and see that 54 is xenon, and then I can fill in xenon. So there is a process you can go through to figure out what, and anytime you have a reaction, if you're missing one particle, you can figure out what it is. Now finally, our third type of emission is called gamma emission. So this means that you are emitting a gamma particle, which is a high energy photon of light. For the most part, this doesn't happen by itself. Usually what happens is if we have an alpha emission or a beta emission, where I'm giving off either alpha or beta particles, I'm also going to have a burst of energy come out, because anytime I do something to break up a nucleus, it tends to be extremely exothermic. So I get that burst of a photon of light coming out, that's a gamma particle. But that usually happens not by itself, but it coincides with another particle being broken off. Now, so alpha, beta, gamma are three main ones, but we can have other ones, okay? We can have positron emission, as we talked about before, where in this case, again, the particle physics behind all this is much more intensive than what we're going to talk about. But in this case, we have a positron that comes out of a proton, turning a proton into a nucleus, blah, blah, blah. If you know what your starting material is, you know it's giving off a positron, then you can figure out what the other particle is that's formed. Okay? So you could write out a reaction like that pretty easily. Here's an example. Potassium-40 undergoes positron emission. If you were told that, you should be able to write the reaction out yourself. You write out the reactant is potassium-40 with its atomic number of 19. You write down the positron that's being emitted. It's an electron with a positive charge. And then you figure out, okay, what's the missing particle? Well, my mass has to be 40. My charge has to be 18 plus 1, so 18. And then 18 is argon. Okay? So you should be able to write from words, if I told you potassium-40 undergoes positron decay, write the reaction, you should be able to do that. Now, we have decay reactions. We also have capture reactions. Sometimes you have cases where a nucleus is hanging out and another particle comes flying in and it gets captured or absorbed by the nucleus. So in this case, if we do an electron capture, that means we have an atom. Again, it has to be told to you what it is. And I'm going to add an electron to that atom. So now both of them are on the reactant side. They're going to be combined into one thing. So if I add the electron to mercury 197, again, it does not add any mass, but it's going to add a -1 charge. So 80 minus 1, my new charge will be 79. That's gold, is element number 79. All right, video's getting long, so that's a good place to cut it off. We'll pick this one up in the next.